ladies and gentlemen. We are lucky today to be able to listen to two world leaders in their chosen fields, Professor Bloembergen and Nicolaas. I would like, on behalf of the Faculty of Medicine and the International Relations section, to thank you both for coming. May I invite now the Associate Dean of the Faculty of Medicine, Professor Tassanavivat, to deliver the opening remarks.
Good afternoon. Professor Nicolaas, Bloembergen, Professor Virgil Murat, and Mrs. Murat Nicolaas, Mr. Christian Chapter, International Peace Foundation, gentlemen, ladies and gentlemen. It's my great pleasure to extend a very warm welcome to Professor Nicolaas Bloembergen, Nobel laureate for physics, and Professor Virgil Murat, Nobel laureate for medicine, to be guest speakers of the event series, Bridges Dialogues Towards a Culture of Peace at Khon University. I would like to thank International Peace Foundation, Faculty of Medicine, and the Institute for Dispute Resolution for the far-sighted vision to support and jointly bring this important event series to celebrate the 40th anniversary of Khon University. I would like to quote His Excellency Anand Panjarachun, former Prime Minister and Chairman of the Thai Advisory Board for Bridges Dialogues Toward a Culture of Peace, who wrote that the dialogues towards a culture of peace invites us to cross borders and build bridges by listening and opening up to other viewpoints, by generating new thoughts and by developing innovative forms of cooperation. This can lead us to a world in which we will be able to understand each other and globalize world needs, broad strategies for change for future generations. Let us be inspired by the knowledge and wisdom the dialogues toward a culture of peace promise to provide. I would now like to invite all of us to show appreciation welcoming to Professor Bloembergen and Professor Murat to be our guest speakers this event. Thank you.
Now, I would like to introduce Mr. Janice McQueen from the International Peace Foundation to say a few words about this project.
Thank you. Let me say a few words on behalf of Uwe Morawetz, Chairman of the International Peace Foundation. Ladies and gentlemen, dear friends, I have no concept for peace and no solution how to achieve peace, but I know that the first step towards peace is the art to pose the right questions. After the first 20 events of Bridges, which attracted 8,000 participants in November alone, we have been approached especially by students and young people who have been inspired by the content of the events and who want to actively participate in this dialogue process towards peace, which is not something which can be left to the elite of a few, but which needs the participation of everyone. This is why we want to further encourage your input and support, and why we look forward to your questions and suggestions, your advice and guidance in this dialogue process towards peace. I thank the chairman of the Thai Advisory Board for the event series Bridges, His Excellency Anand Panirachun, President Professor Sumul Sakalchai and Khon University, and all sponsors and partners for our fruitful cooperation, and especially Professor Ferit Merat and Professor Nicolaas Bloembergen, who came to Thailand without any honorarium to support the events, and I now look forward to the keynote speech of Professor Bloembergen and his important contribution to build bridges. Thank you very much.
Now, I would like to introduce Associate Professor M.On. Myrian, Head of the Radiology Department, who will give some more background on the life and work of our first speaker, Professor Bloembergen.
Good afternoon, ladies and gentlemen. We are honored to have both Professor Bloembergen and Professor Murat with us today. First of all, I'd like to introduce Professor Nicolaas Bloembergen, who is 1981 Nobel Prize for Physics from Harvard University and University of Arizona from USA. Professor Bloembergen received the Nobel Prize for Physics for his contributions to the development of laser spectroscopy. Professor Bloembergen was born in the Netherlands in 1920 and studied at the University of Utrecht and obtained the philosophy doctor's degree in 1943.
And also, of course, include the medical field and the surgical field, which may be of most interest to this audience. But there are many other applications, and we shall give a brief historical review of those. Now, to begin with, we have to explain the word laser. Laser stands for light amplification by stimulated emission of radiation. So it's based on the English language, but actually the word laser is used in most other languages as well. In fact, the Russians used the same word, laser, and in the 1960s there was very good contact between the scientists of the Soviet Union and the United States, and even though the countries were very antagonistic, there was very elaborate discussion and joint communication between the Russian scientists and the American scientists. So what I want to say here is that dialogues in science can promote useful contacts between nations. So I would first like to excuse my introduction of physics. I'd like to remind you what stimulated emission of radiation is. So, because that underlies all of lasers. And if I may have the first slide, then this visible? It's a little dark. Hope you can see it. This gets emitted. Well, I have one here. I hope you can. Well, at any rate, the next slide shows you the other important process. All materials in this room, except the lamps, are dark and they absorb light. And in that case, the electron is raised from an orbit of lower energy to one of higher energy, and one photon is taken out of the incident light beam, and so you get attenuation. And most materials absorb light. But if you prepare the material in a special way so that you have more electrons in the orbit of higher energy, they get stimulated to give off their energy to the light wave that is incident on it. And that is stimulated emission. Now, normally materials have more electrons in the lower orbit than in the higher energy orbit. And you have to do something very special to get laser action. You have to pump the material so that you get more electrons in the higher state. The next slide shows you how this can be done. You start with the electrons in a lower energy state, pump them up to this upper level, and then you get more electrons in that level than in this one, and then you get stimulated emission and gain of the light wave at that frequency. The next slide, you don't have to go very quickly, an energy level diagram of the chromium ions in a sapphire crystal, so that means a ruby crystal, which was the material of the first laser. And you pump them up with a flash lamp, they drop down to this intermediate level, and you get more electrons in this level than in these ground levels, and you get the emission of a red light pulse right there at 694 nanometers. And the next slide shows you the difference between spontaneous and stimulated emission. You may compare it to a huge crowd of people in a marketplace or at a fair, and they walk in all different directions, and they have no order. But with the laser, all the atoms are forced to contribute to the light wave that stimulates them. And that, you see, gets a coherent effect like you have in a marching column of military soldiers reinforced by the marching band, and they all walk in step, and they all emit the light in one particular direction. Next slide shows you how the laser material, which may be a piece of ruby, as I said, with mirrors at the end, initially you get spontaneous emission, but then the light wave that goes normal to these mirrors builds up more and more, and all the chromium ions then are forced to emit in that particular direction. And the next slide shows you really how very simple the first laser was. It was a ruby crystal, which you see here in red, with mirrors made at the end. This one is partially transmitting, so you can get the light out, and you pump it up by means of a photographic high-pressure xenon flash tube. And you get out a blob of light in the red. That was the laser action. Now, why are people so excited? Because the light of lasers is distinguished by three characteristics. Next slide. Well, this is another laser. Skip it. Next slide, please. The light has a very well-defined frequency, and in fact, in special cases, the frequency can be so well-defined to 14 or 15 decimal places. And I believe that within the next decade, our standard of time will be coupled to a laser frequency, and will be accurate to 15 decimal places. But clearly, the light is of a narrow frequency range, and that is used in certain applications, as we shall see. Now, the light is also very directional, as you see from this little pointer, and lasers are excellent pointers. And then these two properties combined lead to the possibility of obtaining very high intensities. Next slide. By concentration of the light in space and in time. You concentrate light in space by means of a focusing lens. And because of the extreme directionality of the laser beam, you can focus it with a microscope objective to an area as small as one optical wavelength. That is 1 micron or 1 micrometer, a millionth of a meter. And that is really a very small area. 10 to the minus 8 square centimeters. In this slide, I don't push it that far. I focus moderately to an area of 100 wavelengths, which is about 1/10 of a millimeter. And the energy of the light comes out from the ruby in a pulse as short as 10 to the minus 11 seconds. Very short time. But because all that energy comes out in such a short time, even if you have only 1 millijoule of light energy, very small amount indeed, because a 100-watt light bulb consumes 100 joules every second. So it emits a millisecond in 1/100,000th of a second. It is really a minute quantity of energy. But look what you can do by concentrating that amount of energy in time, 10 to the minus 11 seconds, and in space. A simple calculation shows that you get in the focus for a very short time a power flux density of 10 to the 12 watts per square centimeter. 10 to the 12 watts is called a terawatt. And that amount of power, 1,000,000 times 1,000,000 watts, is equal to the total power output of all electric generating stations on this whole Earth. And imagine all that power concentrated on 1 square centimeter. And you guessed it, all hell breaks loose. Any material gets evaporated and transformed into very hot plasma, etc. And of course, you don't have to go really that high. You can back off and get a little less destructive situation. But that is what is possible with the lasers. And many applications are based on that attainment of high power densities. Next slide. It shows you the logarithmic intensity scale. First, with the Sun and the Venus, hot because you get irradiated by the Sun at 0.14 watts per second, or 14/100th of a watt per square centimeter. Makes you already feel comfortable. Well, at the surface of the Sun, we have like a radiation of 6,000 degrees. That corresponds to 10 kilowatts. That would be 40 watts. Go to much higher than that still. And we get in the laboratory with a laser, short time duration, and well focused, get to the 20th watts per square centimeter. And then you create conditions that occur in an interior star, like body radiation, 10 million degrees per centimeter. But let's back off because those are only scientific approaches and not realistic. Next slide. Look before that happens. Okay. So I should put it. Yeah. All right. So we look before that happens. We get phenomena of nonlinear optics. That the red light beam comes into this crystal and gets transformed into a ultraviolet beam twice the frequency. That is called harmonic generation of light. And just as in an organ pipe, if you blow in too hard, or a string instrument, and you bow too hard, you get overtones. The same thing can happen for the electronic oscillators in the material. They give overtones, in this case, overtone of light. The red light, the second harmonic is in the UV, half the wavelength, twice the frequency. And that is an important nonlinear optic application. Next slide shows you what happens in that pulse of the first ruby, maybe less than a joule of light, and you focus it into the air, and you get a spark. Because the light intensity is so high that you rapidly ionize the atmosphere. Next slide. And in those early days, people measured the intensity of a ruby laser pulse by drilling holes through Gillette blades. And here they say, wow, 5 Gillettes. They didn't talk about joules per square centimeter, but it shows you the power. You could drill holes through a number of metal blades. This, of course, was not lost on military people. The next slide shows you the incredible laser. And people were thinking of sending blobs of light energy to intercept intercontinental missiles. But even today, 40 years later, that is not possible, not feasible. And therefore it says here, for critical lasers see inside the laboratory. This slide I hope to Professor Shadlov, who unfortunately died, but I shared the Nobel Prize with him in 81. And so this ultimate military application is still not feasible. Next slide is, and we now come to applications that are widespread. And the first one is to use the laser as a pointer, as I do here. And it is used here to construct a part of the tunnel for the BART system, the subway system in San Francisco. And they put a little helium neon gas laser here and show on the city. Next slide shows you the little red spot on downtown San Francisco. Now, of course, such lasers are now used to construct all the verticals and horizontals of the big buildings that go up. Every major gas pipeline, sewer line, or oil pipeline are aligned by means of laser beams. Very large in the construction industry. Next slide. I hope you can see these little dimples here. They have a size of on the order of 1 micrometer, on the order of the wavelengths of light. And these dimples were made by focusing a laser with a microscope objective onto a disc, let's say a CD disc, with a little bit of photoresist material. And then the parts which were exposed to the light, you can chemically treat and make a little dimple. And where there is this dimple, you have information of 1 bit, maybe a 1, and if there is no light, then you have a 0. So you can put 1 bit of information onto an area of about 10 to the minus 8 square centimeters. And then you look at the surface of a CD disc, next slide, which is about 100 square centimeters, and then you calculate immediately, I can put 10 to the 10 bits of information on a CD disc by writing on it with a laser. How do I read it? I read it out with a little tiny semiconductor laser. This is also a but this is a big one. But you have small semiconductor laser in every CD player. And it reads these little dimples. that were put on the CD disc. And in fact, you can do 4 times better by going to twice the frequency, half the wavelengths, because then your little dips are 4 times smaller in area. And so now we can put on a high definition CD disc 10 to the 11 bits. Next slide shows you that that is equal to the total information content of the Encyclopedia Britannica, which in principle you could put on one CD disc. And now, thanks to another application of the lasers, this information can be transmitted everywhere around the Earth by optical fiber communication systems. Next slide shows you the principle. You can focus the laser light clearly into an optical fiber. Optical fiber is finer than a human hair. A human hair is 30 microns in diameter. These optical fibers are only 10 microns in diameter. Of course, they break easily, so you have to put them in material around it. But the working part is very fine indeed, and it has an index of refraction profile, so that the index of refraction in the center is a little higher than on the edges, and that is why you get total internal reflection, and the light cannot escape out of the fiber, but goes follows all the bends in the fiber. And these fibers have now been made so long that they distances of 10,000 kilometers all the way across the Pacific Ocean, and the light stays in there. Next slide. This is historically the first optical fiber laid in the streets of Chicago between 2 telephone exchanges. Next slide shows 10 years later, all the major cities in the United States were already connected by optical fiber links. And a few years after that, in 1984, the first optical fiber was laid across or at the bottom of the Atlantic Ocean. Next slide. In those days, to overcome the losses, you had to have substation where the light energy was reconverted back to electronic energy, microwave signals. Those you amplified, and then you went into the next section of the fiber. But nowadays, the systems don't have these substations. All the information stays as a series of light pulses, and you have amplifying sections of the fiber that contain erbium metal. Erbium is a rare earth and has energy level diagram very similar, but with different frequencies to that of the chromium ion I showed. And these erbium doped fiber amplifiers make it possible to transmit optical pulses all the way between Bangkok and the United States without going back through detecting stations like this. In fact, let me read the system that connects Bangkok and many countries in Southeast Asia to Western Europe. That system has a length under sea of 11,000 kilometers, but a total of 39,000 kilometers of cable optical fiber is involved, because the system lands in 34 different countries and has 40 landing points. It contains 2 optical fiber pairs, and it can transmit 20 gigabits, that's 2 times 10 to the 10 bits per second. That means it can transmit the whole Encyclopedia Britannica between London and Bangkok in less than 10 seconds. The highest capacity system is the so-called flag Atlantic system. That is the fiber link around the globe under the Atlantic Ocean between the US and Western Europe. This system cost $1.6 billion US, It took 27 months to lay the cables from 5 cable laying ships, and there were 4,000 permits required from various companies and industries to get this going. It has 6 fiber pairs, and it uses what is known as wavelengths division multiplexing, so that each one fiber can simultaneously transmit 40 signals. And the total capacity of that system is 2.4 terabits per second. That is 2.4 times 10 to the 12 bits. And so it could transmit the Encyclopedia Britannica in about 1/100th of a second to anywhere else. It could also support 200 million simultaneous telephone conversations, or it could transmit 450 high-resolution digital movies at the same time. Enormous communication capacity, which has made our Earth very much smaller and has promoted communication between all nations. Next slide shows the early geography of the first transatlantic. Next slide. And here you see the expenditures on optical fiber systems, and it shoot up, and now we are somewhere there. In fact, there was an overbuilding. We have now more capacity than we quite need technologically. And of course, that may have been partially responsible for the slump in the stock market of communications stocks. Next slide. Let's now turn to another widespread application of lasers, and that is in the metalworking industry. This is a 5 kilowatt CO2 laser. These glass tubes, these big things are just pumps to rapidly pump around the gas mixture so that the system wouldn't melt. But here you have a 5 kilowatt beam of infrared radiation that will rapidly burn anything that comes in its path. And these systems are used to weld underbodies of cars, to drill holes in thick steel plates, and even in shipbuilding. Next slide shows you welding of automobile underbodies, and the next slide shows you an important application that doesn't require any drilling or cutting. What you do, you shine this laser beam by a little mirror and rapidly scan a surface of a piece of equipment. Where this laser beam hits, it melts a little layer on the surface, and then it moves on, and that little molten surface layer resolidifies immediately by heat conduction to the main body of the metal. And what you do here is you harden the surface because of the very rapid melting and then very rapid subsequent cooling after the laser spot has passed. And that is just what you need to get metal parts that have a very tough surface and are resistant to wear and tear. And any arbitrary gear shape, and the cylinders inside automotive engines can be hardened by the use of these laser beams. Thank you. Next slide shows you drilling of holes near the tip of a turbine blade of a jet engine. Those turbine blades are made of a metal titanium which retains its strength at very high temperature. Melting point of titanium is about 2000 degrees. But you want to be, and that limits the ultimate speed with which these fan blades can turn around. But you can gain a little bit by drilling holes so that they cool a little more rapidly, and then the efficiency of a jet engine is increased by a few %, which is economically significant. by drilling laser holes into titanium blades. Next slide, please. Now we go back from these high power situations to the human body. This is a human hair, and with little laser pulses, well focused, you can drill a hole in a human hair. Totally useless from a medical point of view, but it shows you the precision of laser machining, and you can do marvelous other things with lasers on the human body. Next slide. Shows you that you have to be careful. An ordinary lamp gets imaged on the retina and just gives you that image, but a laser beam gets focused to this very narrow point of only a few microns across. Of course, a blue or green laser beam doesn't do any harm here because it doesn't get absorbed, but right there are the red blood vessels in the retina, and that is get damaged by the strong absorption there. And if you look into a laser beam like that, you get easily blinded. But the ophthalmologists use this to make damage not in the point of sharp vision, the fovea, but points here. And they do that to reattach a torn or otherwise loose retina. And the next slide shows a patient in the doctor's office, not in the hospital, and this was already 30 years ago. Argon ion laser, the doctor looks where the thing gets focused by a little helium neon beam, and then says, that is the spot I want to damage, and then he clicks the argon ion laser. Next slide shows you what happens. Here you see all these white dots. They are scar tissue after the laser beam has hit those spots on the retina. And you see there was a tear of the retina in between, and that tear has now been fixed by reattaching the retina on both sides by scar tissue. Next slide shows you another simple example of a surgical procedure, which this is the forehead skin of an 80-year-old man who was born with a wine stain, port wine stain. It was inoperable previously. But thanks to the laser, next slide, his forehead stain was cured, was eliminated. He had to live 80 years before that happened, but you can do this on a 1-year-old child or less. And the basic idea is simple. Next slide. If you have a port wine stain, you have sections of the skin that have too many blood vessels and therefore cause the red color. But in between, you have normal skin. And now you shine a laser in, and the laser light, blue-green light, gets preferentially absorbed by the redder parts. So those rise more in temperature than the parts in between. And you raise the temperature by carefully dosing the laser to above the coagulation temperature. That's where the proteins denature, coagulate, just as when you start boiling an egg, you get that effect. So you kill the cells where the temperature got above this temperature, but in the regions where the temperature never got that high, you keep the normal living skin. So that's a very simple understanding of how that laser treatment of port wine stains works. Next slide shows you how you can, of course, insert optical fibers into your arteries and get even interior of the heart chambers. And this was used, a person who had very poor circulation and oxygen supply to the heart muscle. And in order to improve that, they started drilling holes, not clearly completely across the muscle, but halfway through. And then, due to the damage you make by drilling these little holes inside the heart chamber, the body generates new blood supply to repair that damage, and that is just brings then new oxygen to the heart muscle. Laser beams, of course, can eliminate plaque in coronary arteries and elsewhere, but that is not in clinical use, because it's very hard that while you remove the plaque, you may also drill a hole in the artery wall, which would, of course, not be very desirable. I hope that these examples have shown you that many laser applications are very beneficial to mankind, certainly those in surgery and medicine, and certainly also the global optical communications. And I want to finish with the last slide, where you see two curves, a red curve here, which is dotted from there on, and a blue curve. And the vertical scale is in billions of dollars, US dollars, annual expenditure. Now the blue curve is for the computer markets, the solid-state electronic semiconductor market. And it starts at 1945 when it was discovered and goes on to 1975 when this slide was made. Now the red curve is for the laser market, but with a 17-year delay. So on the horizontal scale, 1983 is here. And of course then they had to dot it because this slide was made in 83 before the future of the lasers. But it is quite remarkable that this economic prediction of the growth of the laser market in the last 20 years pretty much follows. And if you want to know approximately where the laser market is now, you have to look where the semiconductor market was 17 years earlier, that means in 86. And the important point to remember is that 80% of this market is for civilian purposes and less than 20% for military. Thank you.
Thank you very much, Professor Bloembergen, for your fascinating